To welcome everyone to the ABCD-GIS presentation, June 2016. We are happy to have with us today Jude Ntabathia. Jude has been with CGA for some time now as a developer, and we think every CGA employee at some point does an ABCD presentation, and so it's Jude's turn now. He's got some very interesting things to talk about, and with that, I'll turn it over to you, Jude.
Thanks, Jeff. I'm Jude Mwenda, as you heard. I'm a Geospatial developer here at CGA. Hopefully, I don't get into the way of the slides, but let me just move to the side. And so, before I start giving this talk, I'd like to kind of pointers. One, which is basically feel free to stop me in the midway or wherever if you have any questions. And also, if I'm not clear, because I understand there are certain nuances in my manner of speech that might not be very clear, but feel free to pause, and I'll happily take time to explain. For purposes of this talk, I'll basically speak about geospatial features level search, and the talk is kind of split into kind of four core areas. One, which is basically why exactly feature search is important and why exactly we are doing it, or why we think it is important. Then I'll kind of pivot a little bit to the approaches we actually use to actually provide better interfaces for search discovery, specifically for geospatial data. Then thereafter move towards aspects of temporal representation of how spatial data is also temporally represented and how that could also be affected in search. There's quite a bit of overlap between what I do and what Ben presented a while back, and I think also Paolo will present later on at some point. Then I'll finalize with some of those approaches for data or data extraction, and finalize with something else within the retrospect of feature level search and kind of the learnings in that process. I think most of us here are kind of familiar with the term feature level search, but I think I'll just explain it for some of those who might be listening or listening to this online and might have no sense of kind of understanding of what exactly we mean by features. And so basically, when you look at geospatial data, we're basically talking about layers or kind of form of layers. Now, these layers are made up of small, tiny bits of entities, which basically give us some form of information about, or basically metadata about what kind of data it is, the kind of columns that are actually represented in it, and the kind of form what these entities kind of merge all together to form the actual layer. Think of it as a spreadsheet, that you have this spreadsheet that basically has a series of columns, and each row is basically a record in that kind of entity of this spreadsheet. And so in this sheet, for instance. And so that record is what you're actually calling a feature. Of course, in the broader sense, that entire spreadsheet is what in kind of areas of cartography we consider as a layer or a geospatial data set in one form or the other. So I might use geospatial data set and layer interchangeably. Yeah. And so why exactly is this important? And so I think I'll start back from 2002, 1998, with the rise of the GeoWeb, when all of a sudden there was this, I wouldn't call it all of a sudden, but there was this kind of effort or impetus for people to actually publish and disseminate cartographic data online. The ability that computing actually provided us at that level to actually share and disseminate this cartographic information brought about this kind of huge capabilities which people didn't have before to actually play around with data. And I attribute this specifically to two kind of reasons. One of it is because the improvement in terms of computing resources then. And second thing is also the use of standards, the use of OGC standards, where people could actually share some of these data sets in one form or the other. And we've seen all form of OGC standards that actually help in disseminating these data sets. So you have WMS, Web Map Services, and other kind of web feature services. All these are forms which institutions or agencies were actually basically using to disseminate or share the data that they actually create. And this brought about the rise of spatial data infrastructures, whereby when you're sharing that data set, there is a lot more than just that data set. There is the aspect of metadata. What is this data about? When was it tagged? When was it created? And so there was need to actually build these kind of technological interventions to kind of bring this form of infrastructure where you can actually share not only the metadata, but also the data, and also provide some form of interoperability between these different standards, because we ended up with quite a couple of standards in that facet. And so I'd like to kind of now bring back this whole idea of search. So you have this situation whereby people are publishing all manner of data sets out there, but it becomes almost like looking for a needle in a haystack when you need to search for certain data sets. Yeah, and of course, Google has helped immensely in people being able to discover these data sets. But at times, that lack of context whenever you're searching for data is what, especially researchers who are our main clients in this kind of operation, to be able to kind of put into context the data sets that they actually need to actually be able to do meaningful research. And so this approach or this methodology that I kind of speak about here is basically a kind of first initial step in kind of trying to index all this data from all these geospatial data formats and to kind of provide a nice intuitive interface to provide spatial context when people are searching. Since then, there's need for better tools for spatial data discovery. And I think sometimes we basically rely on serendipity in trying to determine or trying to identify data in one form or the other. And there needs to be a better way to discover some of these data sets. So the approach, and I'll first not speak about specific features themselves, but I'll just slightly introduce the approach in terms of how exactly do you go about this process of indexing all these services out there. How do we make search in such a way that not only can you search for spatial data in terms of spatial attributes, if you only want data related to the United States or Suffolk County or Cambridge, Massachusetts, there needs, and you basically want to get all data sets related, whether it's flooding, whether it's healthcare, whether it's housing. How do you actually provide people with this ability to actually do contextualized spatial search in a very scalable way? Yeah. At the same time, also, how do we search for metadata? Yeah, within some of these data sets. So there needs to be a better approach for this. And the other kind of interesting question is some of this metadata takes different forms and different data types. And as kind of explained, some of this metadata may be string-based, some of it may be time-based, some of it may actually take number-based kind of or decimal-based formats. How do we index all this in a manner in which, if you're basically searching for numbers, or whether it's time function out of all these data sets, you can actually easily consume all that content in one form or the other. And I'll give a very simple example here when you want to search for a river. And I'll give an example of searching for River Omo, which is somewhere in Ethiopia. And you have a world data set, that basically has all the rivers of the world. And it's expected that among one of those features, you'll actually find a river named River Omo. On the other hand, you could actually have someone with just a data set with River Omo clearly mentioned or clearly tagged, or part of the metadata and part of the attributes table. And basically, that is most likely going to come up in some of the already existing search interfaces. And so this brings back to the whole idea of geospatial feature search, the fact that we do have attribute data or metadata embedded within some of these huge data sets, which could be helpful or improve the general discoverability of data in one form or the other. And that's why geospatial feature search is important in our context. And so I'll kind of come back home to the spatial discovery challenge. And I'll start with, most of us are very aware of World Map, which is basically this spatial data infrastructure setup we have here at Harvard that basically enables researchers around Harvard to basically share and access data in one form or the other, and specifically cartographic data. And this stack is basically made up of 4 core main areas, which is PostGIS, which is a spatial database which handles most of the vector data, and GeoServer, which also is tied up to this PostGIS database, which is able to serve tiles through which raster data sets which you as students or other researchers could easily access. And then you have a Django, which is basically a small content management system to basically kind of sticky glue all these other pieces together. Yeah? And then you have GeoXT, which is this idea of visualization. How do you visualize all this data and query all this data in a nice intuitive interface? And so the reason as to why I introduced World Map here is basically to introduce the motivations as to why there was need to think about search differently. How do we totally deconstruct this problem of search and spatial discoverability. And I'll take you to this current world map search page, which basically is this nice table and one search bar. And so when you want to search for, let's say, a river, which is part of a feature set down there, it doesn't give you that capability to actually get those feature level details. And the search is very rudimentary in the sense that it only looks at the top level abstract or metadata levels, which is basically the title and the abstract. And in this context, you do have a challenge where when someone misspells certain names, there is no fuzzy matching in certain contexts. And that ability to discover is basically greatly hampered in that process. And so there was this need to actually think about what is a better way to actually provide search in this interface. Yeah. And I think I'll just introduce a little bit something which Ben and Paula have been working on, which is basically Hypermap, which basically is kind of this new approach in which you not only provide spatial context, but also provide this ability to actually discover data in one form or the other. And so this is basically the kind of first initial step in this process, whereby we first started by taking all the world map layers and actually indexing them into this high fidelity Solar Core. Solar Core is basically this very excellent search indexing interface or infrastructure, which I think David Smiley spoke about here last week, or the last ABCD.
Yeah. Yep.
So I'm just building up on whatever he actually just spoke about. And so it's because of that that you're actually able to get very good search results in this context, and also the ability to actually get this heat map. And so the motivation behind this was basically to provide not only this spatial temporal context, but also a good ability to actually be able to play around the data. Where are areas that are data rich and which areas are data scarce, whereby there isn't much data about this area. So that if you're looking for data, let's say in Australia, you'll actually know we don't have that much chance of actually getting data in Australia from all these services that have been indexed. Yeah. I won't dwell so much time on Hypermap still because it will be presented later on at some point. But Hypermap has its own interface whereby it goes out, gets all these web services, indexes them, gets all the relevant metadata from it, and then basically dumps all that into the core. So that core is what is enabling us to have this better search interface for discovering geospatial data. And so what about features? What exactly makes features special from these layers? And so I'd like to kind of introduce this conundrum that exists, whereby we have already these layers from all these different web services out there that are already indexed. And what we are indexing are basically metadata about these layers, whereby it has metadata, let's say an abstract, a title, certain attributes about it. No, actually, we don't get even the attributes about it, but each and every layer has features. Though remember those rows I was mentioning about that make up that data set, those ones are not indexed yet. So using feature search, this is the first affront to basically not only have this metadata about the layers, but also introduce features as a second level of search that will provide better fidelity search and better discoverability. And so this kind of involved two kind of important things, which is basically having these two high fidelity indexing data tables basically working side to side. Yeah. And part of the process later on in the next steps I'll explain is whereby we'll be merging both the layer search and the feature search to basically bring them together to help you discover data better. Yeah. And so the process basically around this when you're working with world map and external services. So the process involved first starting with world map layers, specifically because these are data sets which we already have metadata and feature level attribute data for them. For other web services, it might be slightly more tricky to do that. But with web feature services, that is possible. But it was better to first start with what exactly is easily available. And so this involved basically going through the World Map API. The World Map API has a very great API that basically publishes all the 20,000 layers that actually exist on World Map. Unfortunately, or fortunately, this layer definition doesn't include each and every feature set or any other feature API that accompanies this. Yeah. So you have this challenge whereby you have to query two different services at the same time. Not only do you have to get the layer metadata, but also you have to get the feature metadata, which was kind of a very nice way to kind of try to play around with these two data sets. Because as you're indexing features, you also need to index certain attributes about the layer to which they belong to. So for instance, a layer could have been produced in the year 1950, and the features don't have any date attributes attributed to them. But as you search for certain features, it is expected that you should know, or the system should automatically know that this feature that you're actually searching for is referring to the time period 1950. Yeah, so there are these two kind of situations whereby you need to put context not only to features, but also to put them in relation to the larger kind of data set to which they belong to, or which is not easy in trying to kind of tie them together. And so, of course, there's the design decisions of using Solar again. Solar is what we were most comfortable with, being able to handle very huge data sets. As like I did a test with the entire world map data set, and it comes to around 20 million kind of individual features that all exist within of all the layers. To be able to actually handle 20 million, to be able to query all these 20 million records at a very high fidelity and get good throughput can be pretty challenging, and that's what Solar does, the heavy lifting for us. And so there's also the other challenge, which is basically because you're basically trying to converse with two different data sources. You have this API that is giving you the layer metadata, then you also have this huge data table or database that is holding the feature level attribute information. You have this kind of processing challenge whereby not only are you hitting the API, but you're also hitting the data table to actually get other attributes that actually belong there. Yeah, and trying to bring them together, then push them to the core. And so you have quite a lot of throughput in between these two. Yeah, and which requires quite a bit of multi-processing. So initially, the initial batch took around 4 days to actually get everything in there. But we recently just introduced quite a bit of multi-processing and multi-threading just to enable things to happen in parallel so that we don't have to wait for 4 days. And so this is kind of like a quick hack which was basically done. And it kind of goes over this whole idea of conventions of configuration, whereby we have this core which basically has all features already seated in there. And basically what I did was, because initially we were using an OGP client to actually render all these features, just put it on top of this standard way in which you're representing these feature sets and be able to put them on a heat map. And I think this is like from one of the features, I think, or just to give move a little bit back in context, this is basically the work that Paolo and Ben have been doing, which is basically on layer level search. So this is what already exists. The ability for you to actually discover layers. There's this aspect of date, which I'll speak about later on in a couple of slides, and the ability to actually query data sets.
This heat map return everything that you're using the system.
Yes.
Is everything. So, but can you explain better what that is the physical location of the data, or is
it's the bounding boxes?
Is the bounding boxes? But this is all worldwide. So it's the bounding boxes of all world and everything that you have. I'm wondering. So what is the return? Is the physical location of the data, like the server where it's coming, where it's located? Or
so I could give you a big spiel about that, but it might sidetrack the feature discussion. Or would you like me to?
Let me just a quick survey. So if you take a layer has, when you get the bounding box of a layer or a huge data set, it's going to be larger than, let's say, one of those features that belongs to that data set. So what you're basically indexing are the bounding boxes of the entire layer in this case. So for instance, you have a layer of, let's say, Cambridge, Massachusetts. So if I get the bounding box of Cambridge, I'll actually get the entire southeast and northwest of Cambridge. Yeah, but Cambridge is made up of features within that data set. So you could have all the public zoos, all the institutions, building blocks, and so on. So all these are individual features, each with its own geometry. And so the other feature search, what it does is that now it goes into each and every feature and gets the bounding box for each and every feature. So what you're doing is you are kind of doing it on both sides. So instead of getting this huge global picture of all the entire data set, you're also able to zoom in into specific features within a data set to actually give you this spatial context within the features themselves.
I see.
Yeah. So I'll just add one note. So there are about 85,000 bounding boxes represented there right now. We've harvested many more, which will be showing up soon. But About 20,000 of those 85,000 are local world map layers. And those are the only ones that we're going to be doing feature search on initially.
So is this extent of the future inside
For
that data set?
feature level search, we'll be searching the extent. No, we'll actually, for features, we're going to be searching the actual, much closer to the actual geometry of the feature.
I'll explain that later on because so what initially the process was to first start with bounding boxes, and then bounding boxes. So I got slightly sidetracked. So simply because of two reasons. You know, when you have a point and you ask for a bounding box for a point, the area you're going to get is 0, and so that brings challenges when you're trying to represent that on a map. Simply because the area is 0. Yeah, and so the better approach is basically rather than to index the bounding box, just to index the features themselves. So the next iteration of this will be basically to index the features themselves, so the geometry of the features themselves, rather than just to index the bounding box. Yeah, so it gives also a slightly better representation of what you want. Yeah. So yes, so the whole idea is basically to enable you not only to search within the data set or the layer itself, but also to search for the features that actually exist within that layer. And so this is basically what I was explaining as kind of a quick attempt to basically just put the data sets from the features themselves within this core and the data. Yeah. So this is kind of a hack. That's why there are all manner of things that don't seem to be well displayed, but you can already see there's quite a bit of data sets from Japan and from San Francisco and so on and so forth. So you're already seeing that you still get a little bit better refinement of the features themselves, not only the layers. Yeah. So it's just a matter of both mixing and matching both of these two search interfaces to actually provide a better method for search discoverability. So I'll come back now to the whole idea of temporal data, and I think I showed on the side, one of the sides of the data set of how to exactly handle the problem or this issue with temporal data. How do you know time when we are not only looking at layers but also with features? So I'll start with the whole idea about the method and the process we did when working with layers or data sets in general. And so and this proves to be very tricky, especially when you're looking for web services out there. How do you know that this was produced in 1920, or does it refer to New York in 1920 or 1930, and so on and so forth? Also, to be able to provide context when people are searching. As you saw in the previous interface, you have this nice time slider that basically enables you to search for layers and data in context. So the whole idea is basically, can you actually tell from metadata that actually is produced, what time range or what time period it was actually produced? Yeah. And so unfortunately, as we all know, as part of the process of publishing data, at times people who are publishing the data are not really so keen to actually make the metadata that useful, because in that particular moment in time when they're creating it, they're more interested in their own needs. They're not kind of thinking in terms of the global context of how do I make this data available, how do I make it easily searchable, and how do I make it easily consumable for others. Yeah? So it's more a question of publish fast, think about discoverability later on, because at that moment of time when you're actually publishing it, you're doing it more for yourself. And so there's actually also this need to actually look at when some of these data sets were published. Yeah? And there's a slight difference between when some of these data sets were published and the exact time they actually depicted. And so a very great example is the NYPL library data set. If you actually go through it, they actually tell you that this was rectified or created on this date, but it depicts 1960 or 1970, and so on and so on. So it adds a little bit of temporal context to that spatial data that you're actually looking for. And so if you're actually looking for New York in the 1960s, or a data set of New York in the 1960s, perhaps someone is doing research on change in New York from 1960 to 1965, the ability for them to actually have this kind of search interface doesn't exist yet. But this kind of a fast approach to try and tackle that. And so, which brings kind of this to kind of process whereby how well do we ourselves also as CGA add time-based data to our own data sets. And so those, if you look at the world map, there are certain two fields which kind of are part of the data set, which are basically temporal start end date and temporal start date, which basically are kind of attempts to give some of those layers that exist on world map context. Yeah. So there are certain layers like the China Ming dynasty, where there are certain rough estimates of those time periods. But that's assuming that, yes, people out there have actually added that metadata, but most cases people will not. Yeah. And so there's need to actually figure out a way in which to mine data from actually the attribute data or the metadata that has been produced. Yeah. So this involved basically trying to figure out two approaches in which not only can we look at the title or the abstract, is there anything else that the title or the abstract or any string-based metadata could tell us about the date in which this was produced? Because you could end up in a situation whereby in the abstract, someone says this was as at 1920 and so on and so forth. But within the metadata specification itself, they have not written anything about date or time, but it does exist in the abstract. So there's need to actually be able to send out these kind of processes that basically are able to mine that data and index that for us. And so this basically took two main approaches. One, which is basically to use the simple approach, which is basically to use a Python regex, which basically checks for certain kind of date strings. Yeah. So what this does is that you pass any string to it and it checks, does this look like a date or does this not look like a date? Yeah. And so this is kind of like the simple minimalist approach to actually tackle the problem. Of course, there is a bigger approach, which is kind of like using NLP and NLP functions, natural language processing functions, to actually determine date. Yeah. And so the reason as to why we started with the regex process was simply because we were just indexing at that moment 80,000 layers. And so we did, first you start with the minimalist approach before you actually determine whether you actually need the NLP approach. I'll give like my conclusions, some of the other kind of insights in terms of that. And so basically using these regex scripts or NLP to basically extract that data. So for the moment, for the time being, you're basically using regex scripts. And so basically then there's also the need to building a custom library. So what this custom library does is we normally have data sets that are normally put in certain contexts. When you're referring to the Ming dynasty in China, because we know that that period of that time during that dynasty, the dates were between 1960 BC to 1950 or 1970 BC. So it's already known facts that there are certain time periods when you're referring to them, yeah, that these were between this and this time periods, yeah. And so at times when people publish data, they are basically publishing data saying this is during this dynasty or this period of time and so on and so forth. So can we actually extract, based on those kind of small nuances in the metadata, the actual time period in which they are referring to? So that's what this library basically does, which it basically just goes out, checks for the Python regex, checks whether are there any kind of date looking functionalities here. And then it's like, okay, yes, I found 2010, I found 2005, I found 2003, and adds them to the index. Then it says, is there anything about any of this list of dynasties or any of this list of time periods that we know of? Yeah. So if it finds Ming in there, it says, okay, this seems to identify Ming as one of those kind of time periods that already existed. Then it also adds it to this list of dates that have actually been mined. Yeah. And so you have this very nice kind of situation whereby you have the series of what I consider authoritative metadata, which is basically this data which was filled in by the people who uploaded this data set. So they might say this was published in 2016, it depicts 2005, and at the same time you also have this other data set or mini data set that basically has a series of dates which basically try and tell you which time period it is. And so in the process of doing such, the date that comes first is actually the date that is authoritative, which is basically what was actually put there by the person who was actually doing the catalog. And so some of the discrepancies, which I think I'll explain later on, is there are times whereby someone has put a data set as 2005 in the metadata, but when you do the mining and you do everything, it refers to a certain time period, and it was in 1950. So between the 1950 and the 2005, which of the two do you have to take? So for purposes of this kind of implementation will basically stick with what the metadata provided, because you don't want to usurp the authority of the person who actually provided that metadata. And so this brought about with a couple of challenges. One of them, which is there are very few date libraries that provide BC and BCE manipulation. Yeah, and they're very small, tiny quirks in which to represent these dates can become very hairy, and you end up pulling your hair. And so I think I gave a very simple example. We would send a negative date to some Python libraries, and it will be, let's say, 005 BC, and it will give you 2005. And so you couldn't make sense why exactly it was giving the wrong date. Yeah, and so this is still very early stage, whereby most of these libraries don't provide that ability in which to handle gracefully some of these very early dates. Yeah, and so in some of those cases, we've had to basically ensure the integrity of the dates is as should be. Yeah. And so basically, I think I just mentioned this. So basically, those challenges of mining this temporal data. One is basically those before common error dates can be very problematic whenever you're mining them. And the second thing, I think I explained this, whereby there might be, for good, very accurate results, which is basically, and I think this perhaps will be the next steps. We will be basically to have a mixture of both these reject scripts and also NLP. Yeah, and to put this into context, there are people in the metadata, they'll actually say 1st January 2005, and they'll actually put January in January. Of course, the reject script will just get 2005, but it will not be able to get the January and the 1st. Yeah, or someone may say on the 3rd of July, and actually write in words 2003 in actual full text words. Yeah, so those are kind of some of the drawbacks the reject scripts basically fails to catch. Yeah, and so in that case, a mixture of both NLP and some of these reject scripts will be able to kind of fill in those gaps or plug in those gaps. I think I spoke about this, which is the inconsistent date values, whereby the question of authority, yeah, and what exactly you suggest or you think the time period of that data set is. The good thing is all that data is being indexed, but when you're actually doing the search interface, there's one date which is actually, if it's not from metadata, then you get the mine date. So I'll try and kind of come to close here by speaking about Gazetteers and why did I put Gazetteers here? This is to bring back the point home about feature level search. How can we move this spatial temporal search that has already been happening to the layer level to the feature level? Yeah. And so within World Map, we have around 7 layers which are actually within the Gazetteer. And some of these layers, only 3 of them have well-defined time dates formats. For context, a Gazetteer is just a geographic index or library or dictionary, which basically is basically a pointer of other things that basically refer to a certain geographic space. And so part of this, some of these Gazetteers have very excellent data in terms of temporal data. And so part of this process is that after pushing all these layers or all these features into the core, there's need for us to actually go back and check the Gazetteer for all these features that have already been added to the Gazetteer and check what time dates or what time periods are they referring to. So you're adding another level of complexity of not only are we having the dates, the top layer date that is related to a specific feature, but also now adding date or temporal functions to specific features themselves. Yeah, and so this work is basically complete, but it's not yet been indexed. So it's what is going to be the next steps. And so one main challenge with this is that there's need to conserve metadata whenever you're actually doing this indexing. And I think I'll try to explain this in a very great manner, in the sense of you have this first run whereby you are indexing all the features, all the columns, or all the attribute data, character varying attribute data related to these features. Yeah, so you have River Omo plus another, let's say, other attributes, like let's say in which geographic kind of administrative area it belongs to, and all other forms of string-based attributes. Yeah, and so you have this Gazetteer which doesn't have that kind of data. So trying to override the Gazetteer from what already has been indexed of the features, you end up losing a little bit of some of that attribute data from the layers. So the only way, or one of the approaches that we've taken to handle this, is to basically fetch the feature or the specific feature specification from Solar, then simply update it with the relevant feature date as depicted from the Gazetteer. And so I'll just finalize with next steps of maybe kind of new things, basically to kind of advance this part, which is basically one which I mentioned. Solar has its own quirks, and so initially when you're trying to index 20 million records, you end up you might end up with a 32 GB or even higher, or 50 GB. And so you had to play around with certain variables like resolution. So for you to actually see that map that you're actually seeing there that paints that picture, there are certain small variables like resolution that actually help you kind of reduce the amount of size of this huge index. Because what it does is that basically it looks at these variables and says, oh, you want me to index this bounding box at a 1 meter resolution. So it means it takes a lot more space to create this index. Yeah. So we had to play around with that and actually reduce that to 1 kilometer. Yeah. To actually see whether we'll actually reduce space. And that was one good way in which to reduce space, because the first kind of batch, it ended up taking around 32. And I was not even halfway through all the layers. And it was kind of like, you continue this, you'll end up taking a 150 GB hard drive. And so kind of playing around with some of these Solar features kind of helps in that process. Second thing now is basically what Ben alluded to, which is basically rather than indexing bounding boxes, yeah, using the actual geometries themselves, yeah, to actually see whether you actually get better accuracy. And the main reason as to why the bounding the box, the geometry itself just provides you the better context or spatial context of those attributes. But I still think for point-based data, you'll still have the challenge of having zero kind of in terms of the area, because the area parameter is what is used to calculate the heat map behind it. But I think the subject matter experts will be able to figure that out in a matter of minutes. Yeah, I think that's about it. Any questions?
So I think the idea of indexing eras, different periods of time, text is very interesting. How did you resolve discrepancies in terms of, let's say, the Iron Age? Not all experts are going to agree the Iron Age starts here and then it's there. So how do you deal with that?
It's funny that you mentioned that, because it's also a huge problem we encountered, because even different, I'll start with the first question. Even before going to that Iron Age, you have this situation where you have how people refer to, how do you convert between BCE to the actual numeric data that you should use for the computing environment. So when you refer to 1950 BC, is it 1949 BC within computing, or should it be truly, because of that zero that is at the middle, it should not be counted? Yeah. So you have this kind of different schools of thought on how to handle that. Yeah. And so for that purpose, I think we've tried to stay away from that, but just using the very exact same value that is actually extracted from the metadata, yeah, rather than trying to do the conversion. For the question about Iron Age, different dynasties, that really depends on whoever is building this dictionary that is basically going out to check these values. So if it's still kind of that question of opinion, whereby it's the administrator who's basically running this will basically determine, I think Iron Age was between this period of time and this period of time. So that is what is going to be fetched. So whoever, the researcher who has a totally different context of the Iron Age may not likely get that data. And so I think that's like a drawback within this methodology.
Just one follow-up question. Do you take other adjectives or vocabulary into account, like early Iron Age, late Iron Age? Is that incorporated?
So that is not yet there yet. For now, we've just basically focused on AD, BCE, and CE, because those were kind of part of the design process. Basically, this is what we need. And so let's start with that. And basically referring to those dynasties. Yeah. But I think it's possible to add that later on and basically improve the library and add those kind of
The
functionality.
dynasties are the only periods that have been added so far. Everything else is just straight numerics and handling the B, and C. And China worked because they're pretty well defined. And we're interested in looking at other lists as they come along.
To follow up on this, I suppose that you could even open up that definition of time periods for the researchers to fight it out.
Yep.
Right? I mean, you can invite users to enter new definitions.
Yep.
Just add to your library. And then if they disagree, right, they can engage in a dialogue and probably even classify some of the different versions too, and let people choose which one works. Yeah. Well, my question to you is that when you're doing the indexing, are you retaining the structure of the attributes for these features? Meaning, of course, features coming from different layers would have a different attribute table, right? Are you throwing all the strings into one pot, or are you defining the attribute item name and then data type and then value?
Yeah, that's a good question. So that was like the initial process was like, should we take each and every attribute and actually add it to this dictionary so that you have a better kind of search interface of both the attributes and everything, yeah? And so basically, the process we did was to basically take everything that is character or string based and add it all into one huge string. Yeah. Initially, the motivation behind that was simply because it was going to be pretty complex to go the other route. Yeah. It is not totally impossible, but when we were starting the process, and I think we also speaking to Dave Smiley, and it was kind of like it was going to be quite a lot more overhead in kind of trying to do that. And so basically the idea was, why not put everything under one string? First get the search interface, how people interact with the search, and then add those attributes later on. But I think it's possible to actually have a dictionary value as part of that. But also the challenge is that some of the data sets that actually live on world map are very, very big. And so, and you're doing calculations for each and every feature set in them. And so you're calculating the bounding box, and then some of them are very huge attribute tables. And so you have to build this dictionary, which you have to push there. It's still possible to actually do that. Yeah. But this was kind of like a quick, easy, slice the margarine approach.
So you're throwing away the numerical columns.
There's only one numerical column that we're keeping, which is the feature ID.
Okay.
So each feature has like, if you took the attribute table has a unique kind of ID with it. So we have the feature ID in it, and then we are putting, and then we are getting all the characters string based.
So if really somebody is interested, they could go to the real structure,
Get back to the record.
get back to the
And always get back to the record. You always get back to the full geometry.
And then also a layer ID, I suppose.
Yeah. So the layer ID is there, the layer name is there, the layer date is there, feature dates are also there. So feature, if you want to know the ones that are part of the Gazetteer, you just go to the query and say, give me all the ones that have feature dates. And it will give you all the features that basically are part of the Gazetteer and or have time-based. Also, one of the improvements that might be done, because I think I noticed this in some of the layer date of some of the attributes, you do have certain attributes that actually have date range. So there might be need, apart from what we are doing now, which is basically querying string attributes and also ID attributes, also query and check whether this attribute is actually of a date type.
Right.
Yeah, so but that's not yet happening, but it's possible. I think I saw one of the tables that had a date range attribute in it. Yeah. And it's not part of the Gazetteer, but you do have some good substantial quite a bit of.
Some layers, not the Gazetteer, but still have contain date as a column. Yeah. So, speaking out loud, so you're having layer ID, feature geometry, date, and then
layer date, and then you have a feature text, which basically a whole bunch of stuff,
everything else,
and it's in Unicode. So you also have like
any language.
Yeah, I think.
So when you search And the return would show the heat map, and when you drill down, you can get to the specific feature.
Yep.
From there to the layer.
And from there to the layer. Thanks.
So I think that some of the problems which you are having in the date could be overcome with NLPs out there. There are strong NLP libraries. And if we can appropriately train our model to recognize the different date types, and I assume that you already have a data set which has date stamps, so we can use that. And as new date formats keep on coming, we retrain our model to recognize those dates. Then these problems might be overcome.
I very much want to do that.
And I think I totally think that might be the best approach to do it. As I mentioned, the motivation, us guys were starting on like, you don't want to fight a mosquito bite with a hammer. And so it was kind of try a very minimalist approach to actually get the proof of concept, get a nice, good data set to do that. But I totally think the next approach would be to use the NLP method and basically do that and actually train a model and actually to able to extract that data.
You could even process your vocabulary with NLP if you want and try to work with that.
Yeah.
So when the indexing happens and it finds anything with the date field, it indexes that as a date field. What if you have in a descriptive field reference to some date?
So like
some text field that someone puts in, this river course existed like this in the year 1242. You're just going to miss those, right? I mean, or is there?
No, if there's 1242, it's going to get that.
So what if then in that descriptive field, someone says, this tribe has 1242 population. What happens with that? You get that?
No, actually, so if it's 1242 in itself, it's not going to get it.
Okay.
Yeah, because there are certain checks it checks for how the date format is actually being put in.
Wait,
so you check for certain values.
Just talking about the feature level. We're not mining at the feature level.
Yeah, like.
Oh, you mean at the
mining-
feature level or at the layer
No,
level?
I'm talking feature level.
Oh, for the feature level, you are not mining at the feature level.
I see. So it's just metadata
Yeah.
at the layer
Yeah.
level.
But
date
the
search.
mining technology could be applied at the feature level.
And right, and then I could see that being one of the issues. I guess
Yeah.
you can find fields that are formatted as date at the feature level, right? And that'd be an obvious one
But your
to
problem
include.
is
It's the
at
same.
those levels. It's the
That
same.
problem is the same.
The problem is the same.
Determining, whether,
A four-digit
1650
numerical,
is 1,650 people or 1,650
Yeah.
a year. And that's where NLP could be really useful. Because right now, if we see 1650 and there's nothing in the metadata, it's probably going to get that as a date, even if it was, there were 1,650 people there.
Interesting.
So it's very crude at the moment.
And then would you do that with 8-digit numbers as well?
No, so,
if you're doing the
we 4 digits,
Is it-
and from 1 to 2016, those get priority.
Right.
If it's, we do go out a little bit into are we going out into the future at all with the miner?
Just until 2030.
We do? Okay.
Another example is that, for instance, someone might put in the metadata 2016 0606 as one huge string.
Exactly. So
And so that is not going to be caught.
But that's
and that's another
standard.
standard date format too.
Yeah.
We should be.
Why?
Oh, and that's what I'm saying. That's like the NLP will be better to kind of process all that. And that's what I was mentioning. You need a mixture of kind of both to actually get this nice data set of all these dates that you're most likely to get out there to train with in the first place.
So then the key is the index. And how often is that built?
I think you just build it once. Are you asking for the frequency or
Well,
the good
right.
thing is that once?
So what if I upload a huge layer in world map?
Yeah.
When does it get into the index and become searchable, right?
Yeah.
It will get put. It will start a process to get pushed right away.
So it'll be an automated
Once this
process
is in
that gets
production.
built into the final system. And then how do you attempt to do feature level search beyond what's in world map?
Oh, you mean?
Just with any
Remote
Any
shape
remote
file that's out
service.
there on
There
the
is
web
no-
or a remote service?
Well, WFS is the beginning of that.
Yes.
harvest.
we'd have to be pulling
You'd have to
WF.
harvest and index everything.
WF. Yeah, I mean, using web feature services,
Yeah.
you could pull an initial cut of features. I mean, you know, my guess is it doesn't make sense to go down the road of harvesting all the features from every layer and every server. You know,
It would make my job easier when someone, you know, do you have park benches in Singapore, right? I can just search and say, yeah, this layer has this layer, so here's 15 in this layer.
yeah.
But you can
Well-
search with this system. You can eventually find the data with this system, at least.
Well, I mean, this is supposed to make it easier to
Yeah.
just find the data.
And
On a
then-
remote
then
server.
you can use the remote server service.
And then if it exposes WFS or Esri feature service, there's no reason why the client couldn't just start querying that stuff.
So can I ask you a question about statistics? So now that you get all those data around the world, so can I know, I mean, I guess you have statistics about where this data come from. I'm just wondering if I want to know who's the most, which country
Yeah.
those data come from.
Yeah, so that's a great question. So that's the kind of
Because
thing
you should have those data.
we should, but right now the index is not by any means comprehensive. It's sort of arbitrary based on the endpoints we've harvested so far. But I think absolutely once, well, at any point, I guess. I mean, we could have a capability that broke content down by predominant. Yeah, I mean, we could come up with automated ways to generate statistics on whatever we have in the system at a given moment. We just haven't had a chance to get to that.
Because
It would be nice to see, because definitely there'll be a huge variation from now in 10 years.
Yeah. And to be able to look at
Yeah.
that over time.
Oh, yeah.
You see, right now probably there's still many people that have server and they use their own server, but no, in 10 years probably
Yeah.
there'll be these huge
Yeah.
farms.
So much more information.
Oh, you're talking about where the server is located.
Yeah, the server, where is the server? is
Well, we know the domain. We don't necessarily know. We haven't been geocoding the servers. Is that what you're saying?
Yeah.
That's interesting. All kinds of stuff
Yeah.
becomes
Yeah.
possible when you have a registry
Yeah.
of where pretty much everything is. There's a million great research projects that come out of that. But you're just touching on a couple of them. And then looking at how that changes over time.
What happens when you find something in a protected layer in world map that's, you know, permissions are
Oh,
locked?
so, you mean at the layer level or at the feature level?
I guess either.
You don't have feature level lock in format, right?
No.
No.
So that is like the
Yeah,
disclaimer.
yeah,
So it should like
I guess
carry from the layer level.
You find it and you can't download it because it's not, permissions aren't open, right? I guess.
Oh, they
Would
don't
you
even
include those
participate, right?
items in your index? I guess.
But I think they
So-
do get indexed.
So
They all
if
get
you-
indexed.
if you-
Yeah.
Yeah, I mean, everything gets indexed, but it's got a padlock by it if it's
Yeah.
private.
So-
And it doesn't display, and you can't get to the layer page.
So at least
But
it's
it
discoverable. You can find out
It's discoverable.
who has it.
You can
and then-
see that.
Right, and then you
Yep.
can contact them. And say,
Oh,
hey,
so you're actually exposing the attribute strings.
We're encouraging people to collaborate.
Wait. If I have a layer, which in the attribute table contains sensitive strings I don't want people to see, you're actually exposing them.
If it's in the title.
No, I mean attribute column.
Oh, not in the attributes. No.
I think
You're
they're
searching
being.
the
Yeah,
attributes.
and that's what I'm saying. This
No,
way they're
well,
being
he might
exposed.
be right
Yeah.
now, but we're not going to be. No, we're not going to expose stuff that's private. So
Yeah, and
once
that's
this
why-
gets to production, we're not going to be exposing private
But,
features.
but what's the mechanism then to come out?
So
We
the-
know what's private and what's not because it's our server.
But once you break it into a feature level search, right?
No, what I'm saying
Everything
is
gets indexed.
we're not going to index private layers.
So they just won't show up in the search.
yeah,
They won't
and that's
show
what I'm
up
saying.
as
They won't
search.
show up on the search. So if the
Okay.
layer is kind of private,
Okay.
we could still.
When we harvest, we
Yeah.
have to check permissions.
Yeah.
We're not doing it now, but when we go to production. and
Okay,
that kind of thing.
okay, so you throw away your current index and you re-index.
Yeah.
When you re-index, you only include the public layers.
Yeah.
So that has a dilemma though, because what if I'm the owner, right? I'm the owner of my data.
Yeah.
And I want to use this tool.
Well, the tool being data's discovery, you don't really need, you're not hampered by not being able to discover your own data. It's for data discovery. I mean, it's making a
If
small,
I get that very huge layer, I want to find.
well, then we'd have to have
You have
private
other
logins
features,
and
yeah.
private
Yeah, that's what I'm.
search and-
Yeah, I'm not saying this is wrong. I'm
Which
just
is possible.
sorting through like.
But right, if you're a private researcher, you've got 100 layers in world map, you don't want to make them public, and you want all the goodies, you want all the ability to search. My thought at the moment is, too bad.
But you can still search for
If
them.
you
Yeah.
want that capability, make them public. But if you,
What about the Harvard
But-
user
but-
level ownership?
yeah, then, I mean, then we could have, we could get into authenticated search and all that. So some people would see some things, other people would see other things. If we get funding for that would be great. I could imagine that being a good grant to go after, to make this work in an environment that
You
isn't all
actually-
where everything is in public.
Yeah, you actually index everything, but
Right.
when you do search,
Yeah.
you check the
Those
authentication.
permissions, yeah.
And return the part of search that.
Yeah, and there's some nice ways to do that.
Yeah.
Just-
Can I ask on world map what sort of percentage of layers are private, or what percentage of people, or just what
It's a
kind of
good
scale?
question. Off the top of my head, I'd probably say about 5%, maybe less.
Private.
Yeah.
I think it's 600 on 23,000,
600 out of 23,000.
if I remember correctly.
So yeah,
Wow.
most people share.
Yeah, that's the next challenge: privacy or permissions and such.
Yeah.
And some of these private are only private temporarily. Eventually they'll be public.
Right. They'll be private while the paper gets written, and once the paper gets written, they might want to point to it.
Can I ask another
Hmm.
curiosity? So you mentioned the World Map API. So it's basically this one. So is this our API?
Oh no, it's not the sole API. So World Map has its own kind of API that shows you all the layers, all the data sets that actually sit on World Map, and it tells you which permissions they have, who's the owner of this layer. That's how I'm able to know, for instance, this feature is owned by this person. So there are certain attributes that I also put to this feature, which is basically this feature is owned by Jeff Blossom and so on and so forth. So each and every all that's being from the
So you
API.
expose the metadata within the World Map, but it doesn't expose the geometry, right?
Yeah,
Of the
yeah.
data itself. Please.
So it doesn't expose the
It's
geometry.
possible in one day to consume data that are in World Map as a geometry and consume this data as a JSON or in another
To
environment.
pick a layer,
Yeah.
hit world map, pull that data out as JSON.
It's still possible because I remember
Yeah.
that we did, and we did just server,